We're now going to look at some applications of differential equations. In fact, looking back at week 1, the reason we spend a lot of time studying differential equations, spending a whole course on them in fact, is because they can be used to model a variety of scenarios in other disciplines, as well as situations in mathematics itself. So it makes sense to look at some applications early on to see how we can connect the ideas of differential equations with these various applications. A classic application of differential equations arises from physical chemistry, where we look at material dissolved in water or some other fluid. And the idea here is that we have some kind of tank, and water's coming in, and water is coming out of that tank. And what we can imagine is it starts off fairly clean, but we're told that there's going to be 250 grams, or a quarter of a kilogram, per liter of salt as a concentration coming in. And it's being mixed in this vat, and then it's coming out the far side. What would happen then is you can imagine if this started clear, then gradually over time, there would be more and more salt. And if you think of the salt as sort of mud, then you'd see it getting dirtier and dirtier over time as more and more water comes in. But then what happens in the long run? Does it stabilize? Does it keep getting worse and worse? Can we predict how long it'll take to reach different levels of contamination? That information is exactly what we get when we build our solution to the mathematical model we're about to create. So let's examine this piece by piece. We've got the concentration of water coming in. We're told that the water itself is coming in at R liters per minute. So we've got several rates going on, which points to derivatives. The well-stirred mixture is draining from the tank at the same rate, R liters per minute. Now, let's see how we can build a differential equation from this. This is a classic kitchen sink model, where what's happening is we've got material flowing in and out, and the net rate of accumulation of the salt in here is going to be the rate in minus the rate out. What we'd be looking at is measuring Q. So what's changing? Q would be the amount in grams of salt in this tank. Let's actually make it kilograms, just to make the units a little bit nicer. So 0.25 kilograms. These are judgment calls you can make along the way. They have no effect on the final answer except what the units of the final answer would be. So Q is the amount of salt, and it's changing with time. And that points to our goal, which is to find Q of T equals. What's the formula for the concentration of salt in this tank over time? Well, what we've been informed about is rates in and out. And so the net rate of change would be the net rate of salt change per unit time. That would be a natural derivative, dq dt. The units of that are going to be a helpful guide here. Q units are in kilograms of salt, and dt, well, we're talking about flow rates per minute, so let's have minutes in there as well. So the derivative is kilograms of salt per minute. How quickly is that changing inside the tank? Then we can look at the individual rates that make up that net rate. The rate in is perfectly specified. We've got a flow rate of water, and we've got a concentration, and if we combine those two in the most obvious way by multiplying them, we take R and we multiply it by 0.25, then this is in liters per minute. We multiply that by the concentration of the water coming in salt. This is in kilograms of salt per liter of water, and lo and behold, we get kilograms per minute. So the units work out perfectly for the rate in. The tricky part is the rate out. Clearly, how fast the water is flowing out has an impact, so that's something that'll play a role. The challenge is, what's the concentration? That's the missing ingredient. We had it for the rate in, but we don't have it here yet. What's the concentration of the water coming out? Well, this is going to vary. This is going to depend on how dirty the water is. If it's not so dirty, the concentration is lower. If it is dirtier water or has saltier water, then the concentration is going to be higher. Oh wait, that amount of salt, or amount of dirtiness or saltiness, is actually given by Q, but we also need it to be a concentration, so we can get that quite easily by taking Q which is in kilograms of salt, and dividing that by the 100-liter tank size in the tank that we have mixed the water in. And once again, the units of R are liters per minute. We multiply that by kilograms and by liters, we cancel and cancel, and this becomes our differential equation. dq dt is R times 0.25 minus RQ over 100. So the rate of change of the salt is going to be dictated by how fast it's flowing in, salt is flowing in, and how quickly salt is flowing out. And we're also going to have that initial condition that at time 0 there's going to be some initial amount, Q naught, and that's given up here. Time t0, there's Q naught kilograms of salt. And so these two ingredients together define our initial value problem, or IVP. Our next goal is to find a formula for the amount of salt in the tank at any time. Well, that is not even code for it. That's exactly what we define as the solution to the differential equation. We have our differential equation, dq dt. Let's write it as fractions because the rest of it's in fractions. 1/4 R minus R over 100 Q, and see if we can solve that. Now, this turns out to be first order, clearly. There's only one derivative, but it is also, we have a choice here. It's linear and it's separable. So the choice is entirely up to you how you want to solve this. Given that we've been looking at linear equations, let's take a look and solve it that way. First step would be to put it in standard form. And once we have it in standard form, we have Q as our unknown, we have the derivative times 1, Q by itself there. Then we would find our integrating factor, which in this case here depends on time. So our m of t is e to the integral of this whole package here, which is r over 100 dt. And that's all constant, so we simply have e to the r over 100 t. Take that, and we multiply our standard form by m of t, by that integrating factor, and we get e to the r over 100 t times q prime, rather than dq dt, plus r over 100 e to the r over 100 t times q. And on the right hand side we have the quarter r times e to the r over 100 t. Taking a look at carefully at the left hand side, it should and is be the product, rather the derivative of a product. And we do in fact see that if we package this as a time derivative of e to the r over 100 times t times q, we get a q prime and a q. We'd have the e to the r over 100t and the factor coming out from the derivative. And on the right hand side, nothing changes when we do that. We simply get the same right hand side, and then we can integrate. With respect to time on both sides. So integrate this with respect to time, integrate this with respect to time, and lo and behold, the integral and the derivative are inverses, so we end up with our exponential times q. On the right hand side, careful what we're integrating, t is our variable, so these are all constants out front, and what we get out of that is 1/4 r is a constant, e to the r over 100t divided by r over 100, and we'll have plus a constant at the end there. That leads to our general solution, which will be q. We're going to divide through by this exponential, And if we're careful, if I divide through by that, it's going to cancel this, and I'm going to have a 1 over that for the constant term, associated with the constant term. And we're going to rewrite that a little bit. The r's cancel here, and this ends up being 100 over 4, and that's it actually, plus c e to the minus r over 100t. We're dividing, or we can replace that with a negative exponent. And that would be our general solution. So far in our problems, that's largely been where we've stopped. However, because we have an application environment here, we can actually go a bit further and find the limiting amount QL. In other words, what does the level of salt go to in the long run? Well, if Q is given by this formula in the general solution, then as t goes to infinity, c e to the minus r over 100 times t is going to head towards, well, it's a negative exponential, r is a flow rate, it's positive. This whole thing's going to head towards 0. So Q is going to head towards 100 over 4, which is 25 kilograms. And does that make any sense? Well, the concentration in the inflow was 0.25 kilograms per liter. The tank holds 100 liters. So eventually, if we imagine our tank here, eventually whatever water was in this tank to start with has been replaced. And so it's all going to be, eventually, all at the same concentration as the inflow water. That's where it's heading towards. And what we get out of this is 0.25 kilograms per liter times 100 liters. How much salt would we have in that whole tank? We would have 25 kilograms of salt. So we get a nice alignment between the long-term prediction that we get from our intuition, that we replace all the water, as well as from the solution, the mathematical prediction of what's going to occur. We get the same answer as if we take the limit as time goes to infinity.